So today we want to know what the force is acting on a flat plate submerged in a fluid. So if I have a flat plate that's nice and horizontal, that pressure acting on the top of the plate is going to be uniform, same pressure everywhere. And so my force on top of that plate, just take my integral, PdA, that's how force and pressure are related. Since the pressure is constant, basically this integral just gives me the area. So the pressure, whatever it is on top of the plate, times that area on top of the plate is this force. This is very similar to what we do in statics, have a uniformly distributed load across a beam or something, and want to turn that into a single point load. So same deal here. I've taken this pressure, converted it into a force that acts right down the centroid. Now a harder case of this is if my plate is not horizontal, because if it's not horizontal, the pressure is not going to be constant anymore. Remember, hydrostatic pressure depends on depth. So the depth of the fluid on top of this part is less than the depth on the part down there. So this part down here is going to have a higher pressure indicated by the bigger arrow, which means that my pressure is no longer constant. So when I do this integral, I can't just say it's P times A. It's something else that we're going to see. That's the point of this lesson, to see what that actually is. Also, in terms of location, I can't just put it at centroid anymore because of that non-uniform load. So to figure out the force on this angled plate, the way I'm going to do that is with a coordinate system that starts at the top of the fluid. So if I have a big tank of water or something, at the top of the water is where my coordinate system starts, and that's going to go down through the fluid at the same angle of this plate. So again, whatever angle this plate's at, the same angle, theta, is what defines my coordinate y. So y goes down to that angle to the fluid, and then that's going to be related to this value h, which is basically the depth of any point that I care about. And so the way I'm going to do this to find my force, I'm going to integrate over this entire area. So I have some little portion dA, I can integrate over that entire thing to give me my entire force. And so what I'm going to end up with is not only the magnitude of the force, I also care about the location. So if I look at this from the top straight down, what I see is this green plate. It's usually going to be rectangular, but I'm just drawing it as any sort of weird shape because it doesn't actually matter. In addition to what that actual force is, I want to find the center of pressure, Cp, because the center of pressure is basically where my single point force is going to go. So kind of like in the previous one, if I had the horizontal plate, the point load goes right in the middle. This is not necessarily going to go right in the middle. It's going to go at some value Cp, which has some y coordinate and some x coordinate based on where this plate is. So now I want to find the magnitude and location of that total force. So start with the magnitude. Magnitude we get from integrating the pressure over the area. So my force is integral pressure dA. Now my pressure is going to come from hydrostatic pressure. So hydrostatic pressure in general can be P0 plus rho GH. So if I have some pressure at the top of my fluid, I have some pressure P0 there. So the total pressure at a certain depth H is P0 plus rho GH. So that's my pressure. And then integrate that over the area. So I can split this up. Rho GH, using my coordinate system, the y's, is rho gy sine theta. So y sine theta is the same thing as h. H is the vertical depth. So if you remember, y is the actual angled coordinate that I'm using. And split this guy up into two integrals. So P0 times dA, and then rho gy sine theta times dA. And then P0 is just a constant, so I can pull that out of the integral. Rho, g, and sine theta are constants, so pull those out of the integral. I'm left with y dA on that guy. Then just like before, since this guy's a constant, I just have pressure times area. And then this guy, the integral of y times dA, is the y value at the centroid times the area. And so what I have here is my force is P0A plus rho g yc sine theta times A, but again, yc sine theta is the same thing as hc, the vertical depth. So there's my equation for the force, the magnitude of the force on the plate, whatever pressure times area I have at the top, plus rho gh for the centroid times the area of the plate gives me that total pressure force. Next thing is to find the location. So to find the location of the force, also going to be called YCP, so Y center of pressure. I want to find the moment that this pressure force is causing, because YCP times that force that we just calculated should be equal to the integral of y times PdA. So here's my pressure force times y. That's going to give me an equation for YCP. So similar to what we did before, except now I have an extra y in my integral. So y times P0 plus rho GH dA. Split that up into two things. So P0 times y, and h is y times sine theta times another y, gives me y squared sine theta. Pull out the constants. So P0 y dA, rho g sine theta, integral y squared dA. This, same as before, is just the centroid yc times the area. So I have P0 yc times a from the first one. Then this guy, integral of y squared dA, you may remember, is the geometric definition of the moment of inertia about the x-axis. So this guy just becomes Ixx, moment of inertia about the x-axis, times this rho g sine theta. Now one thing I don't like about this expression is I have Ixx, the moment of inertia about the x-axis. That's going to matter where my plate actually is. Remember my coordinate system, I can pretty much move x to be wherever I want, so that's not going to help much. What I really want to do is take this about the centroid of the plate. So instead of having Ixx, have Ixc. So instead of the arbitrary x-axis, I want to be through the center of the plate. That's going to make my life much easier. So to do that, I need the parallel axis theorem. So if you remember the parallel axis theorem, if I want to move a moment of inertia, the way I move a moment of inertia is to move it to the new point, and then I have to add on area times the distance squared, the distance that I'm moving it. So if I'm going from the x-axis to the centroid, that distance from the x-axis to the centroid is yc. So Ixx is going to become Ixcxc plus a times yc squared. So that's my new value. And then now what I'm going to do is kind of play with this equation a little bit. So take this term, take out a yc, and then look at this last term. If I distribute this onto here, I end up with rho g a yc, and then another yc out here, so there's my yc squared. So this is basically the last term. Then I'm left with this term, rho g sine theta Ixcxc. The reason I did that, you may recognize this, that's P0a, rho g yc sine theta is just hc times a. That's exactly the expression we got before for the force. So this is exactly the force. And still left with this rho g sine theta Ixcxc. Then what I'm really looking for is ycp. So to find ycp, divide this expression by f. So those f's cancel out. That guy gets an f underneath him. So my ycp, center of pressure, location of this force, is my centroid, plus rho g sine theta, moment of inertia about the x, for the centroid of the plate, divided by that force, the magnitude of the force that I found previously. So what we just found was the y location of the center of pressure where that force can be applied. To be completely specific, because this plate is a two-dimensional object, it's going to have a y coordinate and an x coordinate of where we want to place that force. So to do the x coordinate center of pressure, very same procedure, other than the fact that now I'm multiplying by x inside my integral other than y. So go through the exact same steps we did before. So pressure is P0 plus rho g y sine theta. Now multiply by x's, separate them out. I have x dA, which becomes my centroid, x coordinate, xy dA, which becomes the moment of inertia, xy. Again, parallel axis theorem, turn that into xc, yc, then have an area xc and yc. The second term I can pull out into a force times xc. This first term becomes Ixc, yc, rho g sine theta like before, and then this guy getting replaced by the force. And to find the actual center of pressure, divide by the force, so that guy goes away. I'm left with the x centroid, geometric center of my plate, plus Ixc, yc, rho g sine theta over f, and there's my x coordinate for that center of pressure. So the previous equations are the most general form. They work in any scenario, but a lot of times what we have is that the P0, that additional pressure term at the top, is also 0. If you're using gauge pressure, for example, or if I have a situation where I have that P0 acting at the top and the bottom of the plate. We'll see that in one of the examples that we're going to do. In those situations, it's easier, or we can use simpler equations by essentially just take that P0 in the previous expressions we had, set it equal to 0, and what we get is that the force is the same as my gauge pressure times area, which is just rho g hc. There's my basically hydrostatic pressure at the centroid times area, or hc is also yc times sine theta, so depending on whether you're using h's or y's, either one of those is going to give me the magnitude of the force. Then in terms of location, ycp is again my yc, I xc over area times yc. Similarly, xcp, x centroid, I xcyc over a yc. So first example, we have a sensor array, basically a 5-foot square plate that we want to place out in the ocean to measure some data. So we're going to place it 250 feet offshore. The angle of the ocean at that point is 4 degrees, the ocean floor. So I want to find the total pressure force acting on the plate in that scenario. So solution to this problem, want to find the magnitude of the force. So the force is P0A plus rho g AHC. I want to include the P0 version because I want the total or absolute pressure force of that guy is not going to be 0. So based on this expression, I know all these values. P0 is my atmospheric pressure. I know the area. I know the density of the ocean. I know G. The only thing I don't know is HC, the depth. So how deep is this plate at its current location? 250 feet offshore, angle of 4 degrees. So based on that and geometry, I can find that this depth HC is this distance 250 times the tangent of that angle 4 degrees, which gives me 17.5 feet as the depth for that centroid. So now simply plugging all my values into this equation. P0, atmospheric pressure, 14.7 psi, but I want that in PSF to make all the units work out. So multiply by 144 square inches per square foot. So that's now the proper units times the area. Area of my plate is 5 by 5 squares, so 5 feet times 5 feet. Then plus density of ocean water, 1.98 slugs per cubic foot. Gravity, 32.2 feet per second squared. Area, again, 5 feet by 5 feet. And this HC value that I just found, 17.5 feet. So add all that, multiply all that together, gives 80,800 pounds. So a follow-up question, that previous example. In that previous example, we found the magnitude of the pressure force. Now I want to find where the centroid is. So if we're going to locate that force at a certain point on my plate, where would that point be? So to answer this question, we need the equation for the center of pressure. So YCP is YC, my centroid, plus moment of inertia, IXCXC, rho g sine theta divided by that force F that we just found. So a couple things we need to do before plugging in the numbers. YC, the Y value of my centroid. So I found HC before, the actual depth, but now I want to find YC, this angle coordinate. So again, using geometry, you can find that cosine of theta is adjacent over hypotenuse, so 250 feet over YC. So I can find YC through that. 250 feet divided by cosine of 4 degrees gives 250.61 feet for that. And the other thing I need to know is the moment of inertia of this square plate. So moment of inertia for any rectangle is base times height cubed divided by 12. So that's what I'm going to use for that guy. So plugging in base times height cubed over 12 for I, moment of inertia. I now have all the numbers I need. So plugging in all my numbers, YC I found is 250.61 feet. Base times height cubed, it's a square, so they're both the same thing. They're all 5 feet. So I basically have 5 feet to the 4th power from that guy. Density 1.98, G 32.2, sine of 4 degrees over 12 times the force that we found, 80,800 pounds. So plugging all that in gives a center of pressure value of 250.64 feet, which is not very much more than my centroid. In fact, only 0.034 feet more than YC, which is 0.41 inches. So basically, center of pressure here located 0.41 inches, a little less than half an inch below the actual centroid of the plate. Notice I don't have to do the x centroid value, moment of inertia I, x, y that we see in the x equation. So x equation is very similar, but I have I, x, y. For rectangle, IXY is 0. So essentially all I have is that XCP is XC, the centroid. So again, I can just say 0.41 inches below the centroid, and that covers both X and Y in this case. The next example, have an inclined surface, this green gate under some water, inclined at 30-degree angle. Gate itself is 4 meters long, 5 meters wide, so 5 meters in and out of the page. Want to know what the resultant force is acting on this green surface, so basically from the water and or air, how much force do we have on that grate. So to answer this guy, first thing we can notice is that I have atmospheric pressure, P0, is going to be acting on top of my water up here, but it's also going to be acting down here. So this is open atmosphere down here. So I also have a P0 acting down there. Essentially these two P0s both act on the plate, but they're going to cancel out. So this is a scenario where instead of using the big long equations with P0, I can just call P0 0 because it cancels out anyway. So doing that, I can use the second set of equations. So my force is the gauge pressure times area, or rho g hc times A. Now only thing I need to do is find what this value of hc is. So what is the depth of the centroid in this scenario? So again, here I'm going to need some geometry. I have a rectangular plate. Centroid of a rectangle is right in the middle. So YC is right in the middle somewhere. So basically 2 meters away from point A is where that centroid is. So to get from the top of the water down to my centroid, I go down these 2 meters to point A. So I have 2 meters there. And then I have half of my plate, so half of 4 meters, but I only want the vertical distance. So half of 4 meters times sine theta gives me that vertical additional distance. So that total ends up being 3 meters. So this YC is 3 meters below the surface. So now plugging all that in, density of water is 1,000 kilograms per cubic meter, gravity 9.81 meters per second squared, my depth of 3 meters, and then the area of my plate, 4 meters times 5 meters is that area, gives me 588,000 newtons total, or 588 kilonewtons as the force on this plate. To complete this problem, it'd also be good to find where that force is actually acting, so where is the actual center of pressure for this force. So center of pressure equations, again the version without P0, YCP is YC plus IXCXC over YCA, and similarly for XCP, my X center of pressure. Then for this particular gate, I'm going to need to know IXCXC, which is base times height cubed over 12. Now unlike the previous one, which was a square, this one's actually rectangular, so it matters which one's my base, which one's my height. To figure out which one's which, you need to know where the thing is rotating around. So this is rotating around point A, that's my hinge point. So away from the hinge point is my height, because that's what the rotation moment of inertia deals with. So this, from A to here, that's what my height's going to be. So my height is the 4 meters, my base is the other direction, in this case in and out of the page. So that's my 5 meters. So 5 times 4 cubed over 12 gives me 26.4 meters to the 4th power for I, XC. Again, for rectangles, I, XC, YC is 0. For most normal shapes, rectangles, circles, I, XC, YC is going to be 0. And then my YC, last thing you need to know, so YC value is the value of Y going straight back up here. If I go back up to the top of the water, all the way up over there somewhere, I need to know that distance. And again, through geometry, I know this distance, I know HC, I found that out previously. So just geometry, YC is HC divided by sine theta, 3 meters divided by sine 30, or 6 meters. So it's 6 meters from here, up at this angle, 30 degrees, up to the top of the water. And then finally, XC. XC is the center of my 5 meter plate, so I'm going to call that 2.5, right in the middle. So plugging all this in, I can find YCP, 6 meters for YC, 26.7 for I, 6 meters again, and then my area, 5 times 4. That gives me a grand total of 6.22 meters. Then in terms of X, XCP is XC, which is 2.5 meters. IXY is 0, so I'm basically left with 2.5 meters, again right in the center of my plate in terms of the X value in and out of the page. So what that means is that this force, I can put it at this location here, which is 22 centimeters, 0.22 meters below the centroid at that angle. So if I want to take that entire force, turn it to one point load, that's where it is, 588 kilonewtons acting down at that location.